Namaste students, welcome back to Rama Teaches You. Today we are going to do a new chapter on the D section, D3, motion in magnetic fields. How does a charged particle or a conductor that is carrying a charge experience the force or an effect of that field? How does it move? Okay, in which direction will it move? If you have a certain direction of field, you have certain direction of movement of charge, then the resultant flow, the resultant force will be in which direction? All of these will be answered in this chapter. Okay, let's move on. Okay, so forces on a moving charged particle. Force between two current carrying conductors. First, we'll understand what current carrying conductors are, and then we'll see what happens to them when they are placed next to each other. Okay, so forces between two current carrying conductors. Magnetism originates in the interaction between conductors when they carry current. Okay, so a magnetic field is produced inside a conductor when the conductor has a flow of current inside it. Okay, let's go on. So, what is happening here? Two long aluminum strips are mounted parallel to each other. There is an electrical current in each strip. The magnetic field due to each current interacts so that when the currents are in the same directions, the strips attract each other. Understood? When they are close to each other, then when the current is in the same direction, either in the upward direction or in the downward direction, what will happen? The foils will get closer to each other because of the force of attraction that exists between them. But if the current in both these conductors are in the opposite direction, okay, if they are in the opposite direction, what will end up happening? They will repel each other. Okay, so this is what is happening here. Current in the same direction. What is happening? Look at this. So you have current flowing inwards. That is, what does the positive sign mean? This plus sign, basically current in the same direction. The plus sign means that the current is coming outwards. Okay. Plus means, wait, no. Oh, current into the page. Okay, fine, fine, understood. Okay, we usually write a cross here. That's why I was confused for a minute. So basically, inside this conductor, the current is going into the page. So if I place my thumb like this, using the right hand rule, what will I see? I'll see that the field is flowing in this direction. The field is flowing in this direction. Similarly, the field is flowing in this direction. So you do see a continuum. You do see a continuum of magnetic field like this. Okay, since both of them are in the same direction, what will happen? In this place, there will be a field like this. In this place, there will be a field like this. These two fields, because they are in the opposite direction, look at this. These two fields, because they are in this opposite direction, what will happen? They will attract each other. It's going like this. Okay, sorry, like this and like this. Both the fields are turning like this. Okay, therefore they will attract each other. In this case, look at them. Now the current is coming in out of the page. Okay, like this. Okay, a dot means the current is coming out of the page. A cross means a current is going inside the page. Okay, we don't use a plus sign, we use a cross sign. It is going inside the page. Now, in both the cases, in the middle, what is happening? The magnetic field is in the upward direction. Okay, it's in the upward direction, so we can say that these two fields will repel each other. Okay, so that is the reason why if you have current in the same direction, the two strips will come closer to each other. There will be an attractive force between them. And if these two currents are in opposite direction, what will happen? They will repel each other. Understood? It's all because of the magnetic field that they are producing. Now, figure 2a shows two conducting foil strips hanging vertically. The current direction in the strip can be the same or in the opposite direction. When the current are in the same direction, the strip moves together due to the forces on one foil strip as it sits in the magnetic field of the other strip. When the current sorry, when the current are in opposing directions, the strip moves apart. This effect was the basis for the definition of the ampere until 2019. So, what is 1 ampere? 1 second. So, the definition of 1 ampere becomes 1 ampere is the current which flows through each of the two parallel uniform linear conductors which are placed in free space at a distance of 1 meter from each other and attract or repel each other with a force of 2 into 10 to the power of 7 newtons per meter of their length. Okay, so what is the definition of 1 ampere? If you have a conductor like this, if there are two conductors like this, and in both the conductors there is a current of 1 ampere flowing through them in the same direction or in the opposite direction. Okay, then if they are placed in vacuum, that is the medium is free space, and the distance between these two conductors is 1 meter, then one conductor will put a force of 2 into 10 to the power minus 7 newtons per meter on the other conductor. Okay, so that becomes the definition of 1 ampere. Understood? That is what 1 ampere is. I think we are going to derive it. Let's move on. Now, you can see that this experiment up for yourself using two pieces of aluminum foil about 3 centimeter wide and about 70 centimeters long for each conductor. The power supply should be capable of providing up to 25 amps. So take care. Connections are made to the foil using a crocodile clips. Those basically jumper clips, no? Crocodile clips are the ones that have sharp teeth and you can just place them on top of each other. Okay. Yeah, exactly. Now, the forces on the coil can be explained in terms of interaction between the fields as shown in figure 2b. When the currents are in the same direction, the field lines for the foils combine to give a pattern in which the field loops across both the conductor. Okay, it is surrounded by both the conductor. The notations used to show the direction of conventional current in the foil is explained on the diagram. A cross or a plus sign shows that the current is flowing inside the page, whereas a dot shows that the current is coming outside the page. Okay, now you know that the bar magnets are attracted to each other in this situation. The field patterns for this, okay, the field patterns for the foils is similar and leads to an attraction too. Think of the field lines as trying to be as short as possible. We always know, why do two magnets that are having opposite polarities when placed next to each other want to come closer to each other? The reason for this is that the magnetic field lines always want to be as short as possible. They want to be as short as possible. If they are larger, if they are longer, then the magnetic field lines, what will they do? They will make the objects come closer. They will make the objects come closer. How do they make these objects come closer? They do this by introducing a force. We call that the magnetic force. They introduce a force on these two objects which allows them to move close as possible, as physically possible. Okay, understood? Clear? Okay, let's move on. Now, when the current are in opposite directions, the field patterns do not align themselves with each other. Okay, the field patterns will not align themselves with each other. Therefore, what will happen? The fields will never combine. The fields will never overlap these two conductors. They will always try to be as separate as possible. Therefore, if you want to be as far away from each other as possible, you have to repel each other. So a repulsive force is exerted from one conductor to the other. So you actually see the conductor basically moving like this. Okay, since these two are hanging in vacuum, so if you pass the current, they will move away from each other. Okay, they will move away from each other. Why was this happening? Because their magnetic fields were not aligning with each other. Understood? Now, you know what will happen if the force is large enough? One conductor will be flipped. See, if you place two magnets with the same polarities next to each other, what happens? The one magnet actually flips itself. One magnet actually flips itself and gets attracted to the magnet. Clear? So that is the interesting thing here. The same thing can be happened here also. Okay, so it will somewhat flip it, but actually we never see that experiment because we usually don't allow that much current inwards. Okay, that much current to actually put the magnetic field. Now, next question. Understanding and interpreting field line diagrams can be difficult. Sometimes it helps to think of the field lines as being elastic in some cases. This can be work for gravity and electric field, not just magnetic field. Often this leads to an interpretation of the right forces, attraction and repulsion. So basically, don't think of them as of magnetic fields, electric fields, and gravitational fields as these rigid strings. Think of them as rubber bands. You can stretch a rubber band. A rubber band can be stretched. A rubber band can be contracted also, right? Huh? Similarly, these magnetic field lines, to make themselves as comfortable as possible, they will always try to change their shapes. Okay, they may get curved, they may get elongated. So this can be true for gravitational fields also and electric fields also. Understood? Next. Now, however, field lines are not really elastic lines between objects. The reason it works is because field lines can show the direction of force. When objects are allowed to move, then the work done is the force multiplied by the distance traveled in the direction of the field. Therefore, if the object moves so that the field lines are drawn as being shorter, it is likely that the work has been done by the field and that the object have moved to a low state of lower energy. Sometimes an easy way to communicate a complex idea is not appealing, even if the reasoning isn't quite correct. Okay, so basically what is happening here, again, look at this. When objects are allowed to move, the work done is the force multiplied by the distance in the direction of the field. How much? We know force work done is equal to force times distance. Okay. Now, therefore, if the object moves so that the field lines are drawn as being shorter, if they move, the field lines is becoming shorter. It is likely that the work has been done by the field and that the object has moved to a state of lower energy. So again, just as I said before, the field, the field is making itself shorter. The field is making itself shorter by physically exerting a force on the other object. Okay, it's physically exerting a force on the other object. Thus, the field is doing some kind of work. And why is it doing this kind of work? So that the objects have a lower potential energy as possible. For example, if you place a piece of chalk or a pencil in midair, will it stay in midair? No, it will fall to the ground because the gravitational fields don't like that object there. They want it to lie on the surface of the earth or surface, any surface that is beneath the object. Right? So the pencil will fall down. And when the pencil falls down, we say that earth has done some amount of work. That's what we say, right? Earth has done some amount of work to bring the object to a lower energy. Similarly, the fields are doing some kind of work on the other object to make the object closer so that the potential energy between them becomes as low as possible. Clear? Okay, next. It seems reasonable It seems reasonable that a strong magnetic field, like a strong electrostatic field, represent a large amount of energy stored. The energy can be reduced when the foil moves apart, allowing the field lines to separate too. Again, this has similarities to a bar magnet case, but this time with like poles close together. The magnetic fields can be determined quantitatively too. This is left for later in this topic. So we are going to calculate the magnetic field produced by a conductor. Then using that information, we are going to calculate how much force will these two conductors actually put on each other. Okay, so all of this we are going to learn in the subsequent topics. Let's move on. So forces between a bar magnet field and a current carrying wire. One extremely important case is the interaction between a uniform magnetic field and a field due to a current in a wire. We begin with the field between two bar magnets with unlike poles close together. In the center of the region between the magnets, the field is uniform because the field lines are parallel and equal and spaced parallelly at equal separations. Okay, so if you have field lines, look at this, a north pole and a south pole, all the field lines will have the same magnitude. They will be right. If you place a north pole and a south pole next to each other, okay, then between the space of the north pole and the south pole, you will have field lines appear. You will have field lines appear. Yeah. So these two magnets are placed parallelly to each other. So there will be like magnetic field lines, equally long magnetic field lines from the north pole entering the south pole, right? From the north pole, they will be entering the south pole. Now, what is happening here? Because they are equally spaced, we can say that the strength of the magnetic field between these two magnets is uniform in nature. That is, if you travel anywhere in this magnet, you will experience a uniform magnetic field, and that is a very important thing that we need to have in order to create ammeters, voltmeters, and galvanometers. Okay, anything that has a needle like this is using an electromagnet. Okay, so basically, if you want to make these measuring instruments, you will need to know how these things work. Okay, so let's move on. Suppose a long wire carrying a current is in this field. Figure 3a shows that the arrangement of this direction of uniform magnetic field and the field due to the current. Now, what is happening? Look at this. Current is flowing inside the conductor like this. See, current is flowing in the conductor like this, in this direction. So, when a current flows in this direction, what happens? Look at this. Look at my thumb. The magnetic field is like this then. Okay, the magnetic field is moving like this. Clear? Okay, now another thing. So, what is happening here? You have created your own magnetic field. There is some magnetic field due to the magnets. Now, if you bring this rod and basically try to move it through this originally produced magnetic field, what happens? You have to cut it to go, right? You have to cut the magnetic field to go. So, basically, these two magnetic fields are interacting with each other. Now, when two magnetic fields interact, it creates a force. We have seen it, right? That is the reason why the magnet flips in the first place. Okay, so we know this. So how do we understand this? We can say that if a current carrying conductor is moved through a magnetic field, what will happen? It will experience a force. Why will it experience a force? Because a current carrying conductor produces its own magnetic field. Okay, a current carrying conductor produces its own magnetic field. The two magnets already had their own magnetic fields. Now, these two magnetic fields, when they interact with each other, what ends up happening? They will experience a force. Okay, now the effect can again be explained in terms of the interaction between the two magnetic fields. The circular field due to the wire adds to the uniform field due to the magnet to produce a more complicated field. This is shown in figure 3b. Overall, the field is weaker because the wire that is above it. Now, using our idea of the field lines, the system, the wire, and the uniform field can overcome this difference in the field strength by attempting to move either the wire downwards or the magnets that can cause the uniform field upwards. This effect is sometimes called as the catapult field because the field lines above the wire resemble the stretched elastic cord of the catapult just before it fires the object. This effect is of great importance as it is the basis of the transfer of electrical energy into kinetic energy. So, what are we building towards? We are building towards electrical energy into actual motion. Motion is what? Kinetic energy. So, we are in the process of creating a motor, a DC motor or an AC motor, where what is happening? We are applying a current into our motor. The motor has its own field. Now, what is happening? Because these two fields are interacting with each other, the motor starts to spin. It starts to spin. That is how we create a motor. Understood? Exactly, exactly. So we know, all we had to know was that if two magnetic fields are interacting with each other, they will experience a force. If two magnetic fields are interacting with each other, they will experience a force. And we designed an equipment in order to make the forces rotate a small wheel. And that was the invention for the motor. And because of that, we right now have electrical motors so powerful that they are basically wheels of electric vehicles. Strong, powerful electric motors that allow us to accelerate really, really fast. Understood? Okay, so if you want to study more like DC machines or AC machines, okay, so for example, if you have a field like automobile engineering, electric automobile engineering, so in those cases, you will have to understand how these motors work. Okay, so let's move on. Next. If this effect is of great importance as it is the basis of transfer of electrical energy into kinetic energy. It is used in electric motors, loudspeakers, and other devices where we need to produce movement. Even a loudspeaker, okay, a loudspeaker basically vibrates the diaphragm up and down. Okay, it vibrates a diaphragm up and down so that it can create its own sound. That's how sound is produced in a speaker, by using the interactive principles of magnetic field in the space. Now, is it possible to predict the direction of motion? Obviously, we are going to use the Fleming's left hand rule or simply the vector product of this hand. Okay, like I'll teach you both of this. I personally prefer this one. I usually don't prefer the left hand rule, Fleming's left hand rule, but see, both of them have their own advantages. Fleming's left hand rule will allow us to understand the motion of motors and other DC machines or AC machines much more easily. But for your syllabus, you don't have to worry about machines and all. All you have to do is have a vector product. Okay, the vector product will itself allow you to understand how the force and where the force is going to be applied. Let's move on. Is it possible? Sorry. Is it possible to predict the direction of motion of a wire by drawing the field lines on each occasion when required? But these are several directional rules that are used to remember the direction of force easily. One of the best known of these is due to the English physicist Fleming, as it is known as the Fleming's left hand rule. Okay, so what is Fleming's left hand rule? Keep your fingers like this. Okay, the thumb, the index finger, and the pointer finger, sorry, the middle finger, the index finger, and the thumb should all be perpendicular to each other like this. Okay, it should all be perpendicular to each other. Understood? Now the thumb is the direction of force. Okay, the index finger is the direction of your magnetic field, and the middle finger is the direction of your this thing, current, magnetic field, and force. Clear? I hope this is clear. Current, magnetic field, and force. Okay, let's move on. So, to use this rule, extend the left hand of your. I have just explained this to you. Okay, explaining the motor effect. How does the motor actually work? Okay, let's move on. See, now the explanation for the motor effect has been given so far in terms of field lines. This is, of course, not the complete story. We should be looking for the explanation that involves interaction between individual charges, both those that produce the uniform magnetic field and those that arise from the current in the wire. Electrostatic effect arises between charges that are not moving. Magnetic effect arises because the set of charges that produce the field are moving relative to each other and are in different frames of reference. Their there has been no electrostatic effect because we are dealing with conductor. There have been no electrostatic effects because we have been dealing with conductors in which there is an exact balance of positive and negative charge. Magnetism can be thought as the residual effect that arises when charges are moving with respect to each other. Okay, when a charge moves, what does it produce? It produces a current, right? Whenever a charge moves, it produces a current. Now, with this current, what comes with it? A magnetic field. Okay, a stationary charge can produce a magnetic field. A moving charge can also produce, sorry, a stationary charge can produce an electric field. A stationary charge can also cannot produce a magnetic field. A moving charge can produce a magnetic field. Okay, a stationary charge can produce an electric field. A moving charge can produce a magnetic field. Okay, now what is happening here? See, look at this. So, we should be looking for the explanation that involves interaction between individual charges, both those that produce the uniform magnetic field and those that arise from the current in the wire. We will explain, I think we are going to explain this in more detail in the coming topics. Okay, let's see. As topic D1 and D2 showed, visualization of electric, magnetic, and gravitational fields are commonly used to allow us to imagine the field and its properties. Other representations are those magnetic constructs such as field strength and potential that permit a quantity description of the fields beginning with an inverse square description of the distance. For you, you don't have the potential. The potential section has been deleted for you. Okay, so for you, all you have to remember is the force and the field. Okay, the force and the field. Potential is not your part. Now, these are all ways to model the abstract notion of a field. However, these visualizations have nothing to say about the underlying origin of the fields, how they arise, and how one object can influence another object at a distance. So we are going to understand this. Okay. Wires P and R are equidistant from Q. Okay, both P and R are equidistant from Q. Each wire carries a current of the same magnitude and the currents are in the direction shown. In the wire P and Q, the current is moving downwards. In the wire R, the current is moving upwards. Describe the direction of force acting on the wire due to the wires P and R. Okay, so the current is in the downward direction. Okay, the current is in the downward direction. So the field will be in this direction here. So using the right hand corkscrew rule, the field due to the wire P at wire Q is outwards. See, look at this. The current is flowing like this, and at the position of R, what is happening? The field is coming out, right? The field is coming out. Therefore, due to the wire P, the field will be coming out of the wire. Okay, now next, the at a wire is out of the plane of the paper, and the field due to the wire R at wire Q is also out of the plane of the paper. Again, look at this. Again, this current is flowing like this. It is producing a magnetic field that is coming out. Understood? Now, using Fleming's left-hand rule, the force on the wire Q is in the plane of the paper and the directed towards left. Okay. Now, look at this. Look at this wire Q. Okay. Here, the field is outwards. You point the direction of the field. Okay. The current is downwards. Now, therefore, the field will be in which direction? This direction. Correct? Towards the left. Okay. My camera is flipping everything. But you have to understand the fact that this is the left. Understood? Right? This is my left. Okay. Now, let's move on. Actually, here. Now, next, using Fleming's left-hand rule, the force on the wire Q is in the plane of the paper and directed towards the left in this direction. Clear? Let's move on. A straight current carrying wire passes through two bar magnets. What is the direction of the magnetic force in the wire? Now, first things first, we have to draw the direction of the force like this. Sorry, this is the direction of the field. So, current in this direction. magnetic field in this direction. Therefore, the conductor will be going inside the plane of the paper. The conductor will be going inside the plane of the paper. Clear? See, magnetic field pointed by the index finger, current going upwards. So the thumb is pointing where? The thumb is pointing inwards. Okay? So into the page. Okay? Clear? Next question. A square shaped conducting loop carries a constant current in the clockwise direction. The loop is placed near a long current carrying conductor. Okay, it is placed in a long current carrying conductor. The force acting on the segment XY, okay, XY of the loop is where the current is flowing like this. Therefore, it is producing a magnetic field like this. Okay, it is producing a magnetic field like this. Now, on this plane XY, I'll just do one thing. I'll magnify it as far as possible. So, there is a current like this. The current is causing magnetic field to actually come out. Sorry, come out. So, the magnetic field is actually coming out of the paper because of this movement. See, the current is going like this. It is coming out of the paper, right? Out of the paper. Right, at this point, if the loop were here, then the current would be, the magnetic field would be going inside the plane of the paper. But since the loop is here, the magnetic field is coming out of the paper. Okay, it is coming out of the paper. So what do? The magnetic field is coming out. So place your magnetic field like this. Okay, current is like this. So the force on the line segment XY will be in which direction? Huh? Downward direction, exactly. My thumb is pointing downwards. See, my thumb is pointing downwards, right? So it will be in the downward direction. Okay, let's move on. Okay, directed downwards. The magnitude of the magnetic field. Experiments show that the force acting on a straight wire in a magnetic field is proportional to the length and the amount of current that is flowing through the conductor. Okay, so if you want to increase the magnetic field, what do? You either increase the strength of the current that is flowing in the conductor, or you increase the length of the wire. Okay, all both the things will allow us to do what? It will allow us to increase the magnetic field strength. Okay, so the definition of magnetic field strength differs from those of the electric field strength and the gravitational field strength. We cannot define the magnetic field strength in terms of force upon a charge on a single quantity. Why can't we do that? Force upon charge on a single quantity. Why is this definition such a problem for us? Because we don't have monopoles. In a magnetic field, we don't have monopoles. That is, we cannot have an isolated north pole or an isolated south pole. We can only have dipoles, a north and a south pole existing next to each other, because the force depends on two quantities, current and length. Instead, we define magnetic field strength as force acting on a current carrying element upon the current in the element multiplied by the length of the element. The element is a short section of wire that carries a current and is at right angles to the magnetic field direction. When a force F acts on the element of length L, when the current carrying it is in I, then the magnetic field strength B is defined as B is equal to F upon I L. So F becomes what? F is equal to BIL. Okay. So if you wanted to write it in the vector formula, we usually write it as force is equal to I multiplied by L cross B. I'm going to explain to you the same law of Fleming using this logic. Okay, look at this. So you have a current like this. Okay, this is a conductor. Uh, this is a conductor and the current flowing is this pink color. Okay, and you also have magnetic field that is going inside the plane of paper. You have magnetic field inside the plane of paper. Okay, now dl is this, that dl will always have the direction of current. Okay, dl is what? A small length of the conductor. Okay, so this L value, L will be the direction of current. Now, when we, this is a cross product. You know what a cross product is, right? There are two types of multiplications involved. One, a scalar product, a dot product, or a vector product, or a cross product. Okay, so we know that the resultant of two vectors, the cross product of two vectors is always perpendicular to the direction of both the original vectors. Okay, so what are the vectors here? The vectors in our case are the magnetic field and the current. Okay, the magnetic field and the current. So L cross B, length cross breadth. Okay, length cross magnetic field. L cross B. So what happens? The length is in this direction. It is the direction of the current. And how do you do the cross product? If you have two vectors like this, you have a vector like this and you have a vector like this. This is A and this is B. Okay, so A cross B is what? You first place your hand in this direction, in the direction of A, and then you curl your fingers in the direction of B. So you will get a vector B that is in the outward direction. B cross A will be what? B cross A will be the in the inward direction. That is known as vector multiplication. They must have taught you in class, no? Vector multiplication. Maths, but you must have learned in maths also. Okay, so what is happening here? See, you have current in this direction. Magnetic field is in the inside direction. So you're curling your fingers in the direction of magnetic field. What happens? The conductor is basically the conductor is experiencing a force in the upward direction. Now imagine if the magnetic field were coming out, then the current would be in this direction. The magnetic field, you will have to curl your fingers like this to reach your magnetic field. So the force will be in the downward direction. Now using Fleming's left hand rule, current is in this direction, magnetic field is in this direction. Where is the thumb pointing? Upwards. Now, if the magnetic field is in the outward direction, you point magnetic field like this, you point the current like this, and the downward direction. So instead of using two different rules, if you know how the two vectors are getting multiplied, all you have to do is make sure that the multiplication goes through using cross product. Okay, I basically, since I know the right hand rule, okay, the curling effect, okay, it becomes easy for me to calculate any of these forces. I don't have to break my head every single time. Clear? Next. Okay. The element is a short section of wire that carries a current and it is at right angles to the magnetic field direction. Right? The direction of current is basically perpendicular to the magnetic field and it is also perpendicular to the force. When a force F acts on the element of length L, when the current is in L, then the magnetic field strength B is defined as what? Magnetic field strength is F upon L multiplied by I multiplied by L. Okay, the unit of magnetic field strength is a Tesla. Okay, and we abbreviate it as capital T, like Newton. Newton should always be written in capital N. Okay, whenever you have units named after scientists, what do? We capitalize the first letter. Okay, so that will be T. So this is equivalent to the base fundamental units kilogram in minus 2, ampere minus 1. The Tesla can also be thought of as Newton ampere square upon Newton per ampere meter. Newton per current to SI unit is ampere and length node as I know it is meter. Okay, so the Tesla turns out to be a large unit. The largest magnetic field that can be created in a laboratory is a few kiloteslas in magnitude, and they only for a very short time. The magnetic field of the earth is roughly 10 to the power minus 4 teslas. The magnetic field that is protecting us from the ionic rays that are coming from the sun is only 10 to the power minus 4 teslas. So we cannot use such a huge quantity every single time we are doing our calculation. So what do? The largest fields are associated with some neutron stars where the magnetic field strength can be of the order of 100 gigatesla. Giga means 10 to the power of 6. Okay, 10 to the power of 6 teslas. The definition leads to the force acting on a wire of length L carrying a current I in a magnetic field is given as F is equal to BIL. I think the reason why I don't see any vector product is because they haven't taught you vectors. Okay, but in India, in the Indian textbooks, we learn vectors in 11th class. Okay, and then we start because for us everything is related to vectors. Okay, chemistry, physics, maths, everywhere we see vectors. In maths, we have two different chapters where we study you only vectors. Okay, so F is equal to ILB. In this case, we are assuming that the current, the magnetic field, and the magnetic field and the conductor are all perpendicular to each other. Sorry, the current and the magnetic field are perpendicular to each other. Therefore, the force is also perpendicular. The direction of the current and the direction of L are both the same. Okay, the direction of L, yeah, because length does not actually have a direction, right? Length does not have a direction. Let's move on. The equation applies when the field lines, the current, and the wire are all at 90 degrees to each other, as they are when we use the Fleming's left hand rule. When this is not the case and the wire is at an angle of theta to the line, then we need to use the component of I at 90 degrees to the field. How do we do that? We use that by using trigonometry. Okay, so we know the value of, we see all we need is the perpendicular component. We don't require the horizontal component. So the perpendicular component will be given as something sine theta. Okay, so our whole value becomes F is equal to BIL sine theta. We use ILB sine theta. Okay, now the equation is written in terms of current in the wire. The current is, as usual, the result of moving charges. The equation can be modified to reflect this. We know that the value of current is Q upon T. The value of current is Q upon T, where Q is the charge that flows through the current element in time T. Substituting the values, what do we get? What do we get? We know that current is equal to Q upon T. You're putting the value of that in here. So B Q upon T into L. So look at this. We have F is equal to BIL sine theta is equal to BQ upon T L sine theta is equal to what is length upon time? V. So BQV sine theta. Clear? Q into V cross B sine theta. Okay, the term L upon T is the speed V of the the charge carries through the current element, and making substitution gives us F is equal to Q into V cross P. Okay, for the force acting on the charge Q moving with the speed V at an angle theta to a magnetic field B, both of them have the same meaning. So there are two separate formulas for force. If the current is known, then you will say force is equal to BIL sine theta. If the current is not known, but the movement of charge is known, only the velocity is known, then we can say F is equal to QVB sine theta. It will be QVB sine theta. Notice the way that the angle theta is defined in the diagram. It is the angle between the direction in which the charge is moving or the current direction, the same thing, and the field lines. Do not get this wrong by using 90 minus theta in your calculation. It is always going to be theta. Understood? It is always going to be your theta. Next. So we have learned two formulas, right? We have learned two formulas for force. One is ILB sine theta and one is QVB sine theta. Using this knowledge, we are going to solve some problems. Okay. Now, worked example 2. When a charged particle of mass m and charge q move at a speed v in a uniform magnetic field, then a magnetic force F acts on it. Deduce the force acting on a particle of mass m, charge 2q and a speed 2v traveling in the same direction. So when the force was how much? When the force was basically F, you had what all values? Q, V, when a charge of mass m, charge q and moving at a speed v in a uniform magnetic field, then a magnetic force acts on it. Okay, so why is there an m here? Oh, in the magnetic field, in a uniform magnetic field. Okay, now deduce the force acting on the particle of mass m, charge 2q. F dash is equal to what? F dash is equal to 2q multiplied by 2v multiplied by in the same magnetic field in the same direction. Okay, so F dash will become what? Is equal to 4qvb, and we know the value of qvb is what? F. So F dash is equal to F. Clear? Okay, next. A horizontal straight wire carrying a current of 3.5 amps, a length of 4 centimeters of the wire is subjected to a horizontal magnetic field between the poles of a magnet. A magnetic force of 14 millinewtons acts on the wire. Okay, a force of 14 millinewtons acts on the wire. So we have been given the current, we have been given the length, and we have been given the force. Determine the magnetic field strength, assuming that it is constant between the poles of the magnet. So all we have to do is use the formula. We know that F is equal to BIL. Now, why do we need a theta here? We don't need a theta here because it is 90 degrees already. It's a horizontal. No, see, Akshay, look at this. The field is like this. The current is like this. Both of them are what? They are perpendicular to each other. Okay, so we don't need to use the value of theta. So we know B will be equal to F upon IL. So F is how much? 14. 14 into 10 to the power minus 3 newtons upon 3.5 multiplied by 4 into 10 to the power of minus 2. Okay, so this will become 2 2s are 4, 2 7s are 14, 3.5 into 2s are 7, 2 and 2 gets cut off. This 10 to the power minus 2, when it goes up, you will get 10 to the power of minus 1 newtons, or sorry, 10 to the power minus 1 Tesla, or your 0.1 Tesla. Is it correct? Yeah, 0.1 Teslas. Okay, now let us determine the direction of the force acting on the wire. What will it be? The magnetic field is in this direction, the current is in this direction, so the conductor will move upwards. Okay, sorry. This is right hand rule. Sorry, the current is in this direction. Okay, and the magnetic field is in this direction, so the force will be downwards. It will be downwards. I accidentally used the right hand rule. Right hand rule is for generator. Okay, Fleming basically created two different laws, one for the motor and one for the generator. Okay, so next question. um, an alpha particle of mass 6.6 into 10 to the power minus 27 kgs moves at a speed of 7.5 is into 10 to the power 3 meters per second through a uniform magnetic field of magnitude 0.24 Tesla. The velocity of the particle makes an angle of 34 degrees with the magnetic field. Take out your calculator. Okay, so what will we have? So we know the mass. Why are they giving us the mass again and again and again? Is there a requirement for the? Oh, we have to find the acceleration also. Yes, then it will be required. Okay, so we know that F is equal to what? F is equal to QVB sine theta. Now, they have given us an alpha particle. What is an alpha particle? Alpha particle is a helium 2 plus ion. Helium usually has 2 electrons in its outermost shells, right? If you remove these 2 electrons, what do you get? You get a nucleus with a 2 unit positive charge. That is an alpha particle. So, how much charge will an alpha particle have? 2 electrons worth of positive charge. 2 electrons worth of positive charge. Okay, so we know the charge of an electron is how much? 1.6 into 10 to the power minus 19 into 2. What will you get? 3.2 into 10 to the power minus 19 coulombs. This is the Q. So 3.2 into 10 to the power minus 19 multiplied by 7500 multiplied by 0.24 multiplied by sine 34 degrees. Calculate this. So 3.2 multiplied by 7500 multiplied by 0.2 multiplied by sine 34. What do you get? Oh, sorry. Oh, yeah. How much? 3.2. Yeah, 3.2. 3.2 multiplied by, are you sure? 10 to the power minus 9. So, okay, fine. 3200 into 10 to the power minus 19, right? So, 3200 multiplied by 10 to the power minus 19, or you can write it as 1, 2, 3. No, 320. It should be 320 into 10 to the power minus 19. 3.22 multiplied by your 10 to the power of 10 to the power of minus 16. Okay, this is fine. Now, we need to find the acceleration. Okay, this is the force. We know that acceleration is equal to what? Force upon mass. The mass has been given to us 6.6 into 10 raised to the power minus 27. So if you divide them both, you will get a sizable amount of acceleration. Right, 4.58 into 10 to the power 10 meters per second square. Note that the acceleration is directed at right angles to the velocity, hence the speed of the alpha particle does not change. Okay, the force was being applied at 90 degrees, so the velocity will not change. Right now, basically, Akshay, if you are moving forward, if you are running on the ground, moving forward, the earth is pulling you downwards. Earth is not doing any work to reduce your speed. Understood? Earth is not doing any work to reduce your speed. Okay, so that is same way, because the magnetic field is acting perpendicular to the charge, perpendicular to the velocity of the charge, the magnetic field will not be able to create any work. Even if you have acceleration, it will not be able to create any work on that charge to change the speed of the charge. Okay, it won't be able to change the speed of the charge. Now, force between two parallel wires. In topic D2, the magnetic field pattern due to a long straight wire was described as a series of circular field lines centered at the circle, right? So basically, what was happening here? We just learned this in D2. You had a wire. Okay, what does it mean? This means that the current is coming outwards. So the field lines would always be concentric circles with the center at the center of the wire. So if the current is coming out, all of them will have anti-clockwise direction field lines, right? All of them will have anti-clockwise. If the current is coming outwards, all of them will have anti-clockwise direction field lines. Understood? So the magnetic field strength B for the arrangement when the current is in the wire is given as mu naught I upon 2 pi r. Okay, you don't have to derive this. Okay, mu naught I upon 2 pi r. Now, mu naught is what? It is the permeability, the ability to basically make the magnetic fields flow through the medium. Okay, that is known as mu naught. Okay, so but we already know that mu naught upon 4 pi is what? 10 to the power of minus 7. So mu naught upon 2 pi will become equal to what? 2 into 10 to the power of minus 7. Because if you multiply a 2 here and a 2 here, what will happen? No, no, wait, hold on, hold on. Sorry. Mu naught upon 4 pi is equal to 10 to the power of minus 7. So if you multiply 2 on both sides, what do you get? Mu naught upon 2 pi is equal to 2 into 10 to the power of minus 7. Clear? Other, you can write that in your book itself, or if you're using a tab, you can just create a short note there where you will, otherwise you will not be able to understand, because you know the value of mu naught is equal to 4 pi into 10 to the power of minus 7. Mu naught upon 4 pi is equal to 10 to the power of minus 7. Mu naught upon 2 pi is equal to 2 into 10 to the power of minus 7. So in different formulas, we will use different values. Okay. 10 to the power minus 7. Yeah. See, basically, see, what is the formula for permittivity? What is the formula for permittivity? The magnetic field. Did we learn it? One second. So we will understand this better in a couple of minutes. One second. So the field strength is a 1 upon r law in opposed to 1 upon r square law. Okay, let's see. So that appeals to the point charge and the masses in Coulomb's law and Newton's gravitational law. We can combine this with the expression for the force acting on a wire to determine the forces that act between two parallel wires, where R is the separation between the two wires. Wire 1 has a current of I1 that gives rise to a magnetic field of strength B. This field extends to wire 2, which is at a distance r away from the field. So what is happening here? See, Drupat, this this wire is creating a field on this conductor, due to which what is happening? Look at this. Let's zoom in to the maximum extent possible. There are two forces acting here. Okay, there are two forces acting here, and it's not like both the forces are acting on the same object. There are two forces are acting on two different objects. Look at this. So the current is flowing like this. Okay, Akshay, the current is flowing upwards. So the magnetic field at this point will be inwards, right? So we know the magnetic field to be in this direction. We know the current to be in this direction. Okay, so the magnetic field is inwards, the current is in this direction. Okay, therefore, what is happening here? Wait, the magnetic field is inwards, right? So inwards current. Hold on. Again, I am so sorry, I was using the right hand. Okay, so basically you have the magnetic field in the inside direction, the current, sorry, is flowing on the upward direction. So the field that is provided by the thumb is in this direction. Okay, the similarly you will have the current in this direction. The field is the current is in this direction. The field is basically outwards. So the field is wait. Yeah, the field is outwards, much better. So current upwards, field is outwards, and the force is in this direction. See, right here, because of this conductor, the field is coming outwards. So outward fields, current in the upward direction, therefore the force will be in this direction. Okay, so this force is making the conductor go, this conductor is applying a force on this conductor, which is making the conductor come inwards. Similarly, this conductor is also coming inwards. So there are two forces that are making sure that both the conductors come close to each other. Okay, now let's examine what is actually happening here. Okay, so what is the formula for force on a conductor? Mu naught I upon 2 pi r. Okay, so we can combine this with the expression for the force acting on a wire to determine the forces that act between the two parallel wires, where R is the separation between the two wires. Wire 1 has a current I1 that gives rise to a magnetic field B. This field extends to wire 2, which is at a distance R away. The field strength at the wire 2 due to wire 1 is equal to mu naught I1 upon 2 pi r. Okay, so mu naught I1 is producing the current upon 2 pi r is the force that is acting on the wire 2. Okay, so what is the reason for the cause of the force being acted on wire 2? Because of this field produced by the wire 1. Okay, so the force on wire 2 due to wire 1 will be mu naught I1 upon 2 pi r. Similarly, force on wire 1 due to wire 2 will be mu naught I2 upon 2 pi r. Okay, so what is happening here? Both of them you understood now? Now, wire 1 has a current I1 that gives rise to the magnetic field B. This field extends to the wire 2, which is at a distance r away. The field strength at wire 2 due to wire 1 is mu naught I1 upon 2 pi r. The current I2 in wire 2 interacts with this magnetic field. Okay, so the magnetic field experienced by wire 2, the magnetic field experienced by wire 2 is how much? B is equal to mu naught I1 upon 2 pi r. So this conductor, this wire 1 is producing a magnetic field, okay, due to this current I1 at this particular point. This is the distance r. Okay, now understood this one? Now the force exerted on the wire 2 has a current of I2. Okay, wire 2 has a current of I2. So basically force is what? I L B, or simply BIL. BIL. So B is how much? Mu naught I1 upon 2 pi r multiplied by I2 multiplied by the length of the conductor L. Understood? So force will become equal to mu naught I1 I2 L upon 2 pi r. Now, similarly, Akshay, for the wire 2 is producing a current, the magnetic field experienced by wire 1. The, okay, one second. The, the magnetic field by wire 1 is what? Due to 2. So, B is equal to mu naught. What is the current flowing in the wire 2? I2 upon 2 pi r. So the force experienced by wire 1 due to the magnetic field of wire 2 F is equal to, this is, let us call this F1. Okay, so F2 will be equal to how much? B, again BIL mu naught I2 upon 2 pi r. Current in the wire 1 is I1 multiplied by L is equal to mu naught I1 I2 L upon 2 pi r. Both the forces are the same. they are the same, but the direction is in the opposite direction. I'm so sorry. Again, you're telling something. What? என்ன சொன்ன? Same force, but in the opposite direction. Correct. Okay. Now, these two forces are responsible for bringing both the objects together, right? These two forces are responsible for bringing both the objects together. Now, let's see what is happening due to this. Now, F is equal to how much? Okay. Now, consider the force per unit length on wire 2 rather than the total force on the whole length means what? Therefore, force per unit length. Okay, what is force per unit length? We know that F is equal to mu naught I1 I2 L upon 2 pi r. Therefore, force per unit length will become mu naught I1 I2 upon 2 pi r. This is known as the force per unit length experienced by the wire on due to the other wire. Wire 1 due to wire 2 or wire 2 due to wire 1. This is the force per unit length on wire 2, which is measured in newtons per meter. The same force per unit length acts on wire 1 due to wire 2 as a result of Newton's third law. The constant mu naught is known as the permeability of free space, and you can regard it as the response of vacuum to the presence of magnetic field. It has the value of 4 pi into 10 to the power minus 7 newtons per ampere, which is 1.26 into 10 to the power minus 6. The unit of mu naught can be expressed in Tesla meter per ampere. The unit of mu naught is Tesla meters per ampere. Understood? Okay, 1 second. So, students, we are gonna end our class here. We have almost finished like approximately 50% of this chapter. Okay, only 10 more pages are left. Rest are questions. So in one or two classes, we will be able to finish the complete chapter. I really hope you like my explanations, the way I teach. Sometimes, usually, I make some mistakes. I'm so sorry about that. Okay, but I really hope you enjoyed my video. And if you liked it, please like, share, and subscribe. And if you have any doubts in the question, or you want me to teach you any particular topic in the IB section, you can comment down in the comment section. Okay, thank you and have a nice day.